Coming to next slide, which is on design process. Okay, so since we discussed from on different types of layouts and components, now you can it's more or less putting down in the chronological order which you want to do first. Okay, so first, in any, if you're working in a company and you are a cooling system engineer and somebody gives you a vehicle and asks you to design a cooling system for this EV, first thing which you should ask is that, tell me what is the heat rejection of the components. Okay, you have different components. You have battery, you have e-motor, and different components. So each components generates heat. They add heat to the system. First thing you should do is that you should get the list of components and amount of heat they add. Okay, so that's the first step, estimation of battery heat rejection. Sometimes battery suppliers can give us this data, or sometimes we have simulation tools which will generate this heat generation map based on battery chemical properties and battery properties. So this can be done. So it's estimation of battery heat rejection plus e-powertrain. I think I missed it. Plus e-powertrain. Okay, e-powertrain components, EPT. I'll try EPT. E-powertrain. And coming to the next step, once you found out how much heat you need to reject. For example, if it's 10, if you need to reject 5 kilowatts, or if you need to reject 20 kilowatts or 100 kilowatts, based on the amount of heat rejection or based on the capacity of the battery, you can choose which kind of heat exchanger you need. Whether you need air cooling or whether you need, maybe I can show you the slide. So whether you need air cooling, whether you need a liquid cooling, or whether you need a refrigerant cooling, or whether you need a combination of both. So these kind of decisions on which type of heat exchanger to use, you should take as the next step here. Okay, on heat exchanger selection. So first up, you find out how much heat is there, how much heat you need to remove. Then you select what device, what component you need to remove the heat. Okay, if the heat addition is less, you can cool with air. If the heat addition is more, you can go with a coolant. If it's very high, you can use a refrigerant. Okay, it depends upon the strategy. You can use valves, those things as we discussed in the previous slides. Okay, heat exchanger selection is the next step. And third step is coolant flow rate estimation. Okay, now we have decided to use a heat exchanger. So next you should decide how much coolant flow rate is required. Okay, coolant that needs to flow through the system to remove the heat. Okay, so it's basic heat transfer fundamentals which you can see in your essential books or those books. Mostly convective heat transfer is being followed here, so it's a basic theoretical exercise which you can do. Battery, so it's having a heat of battery surfaces rejecting a heat of around 5 kilowatts. So how much flow rate required? So you do a simple MCP delta T calculation where you find out flow rate required to cool this battery. Okay, so these things I didn't really discuss in detail on the calculation part here, but it's something which you can always refer to in your books. You estimate the coolant flow rate in the system, in the circuit, okay, which will flow through all the components. Next is, once you decide the coolant flow rate, you will come to the sizing part or packaging part. It's a very, very important section where we face a lot of issues in industries where you will not have enough size in the vehicle to fit all the components. Okay, so that's why in small cars we generally use a series loop. Okay, where this is a very short loop and a compact loop, compact circuit which you can easily fit inside a vehicle without much difficulties. But when you want to use bigger circuits like this, you need to have a lot of space. Okay, so even based of these strategies, we decide which type of coolant circuit to use. Okay, so it's come down to packaging, how much size is there and how do you route the hoses, because it's a very congested space we'll be having in the vehicles. And next is coming to component sizing. Here you will be saying how much, so you will select I need a radiator and not a chiller for the circuit. Then comes the question, how much size big the radiator I need to use, whether it's a big radiator or small radiator. Generally these decisions we can give input to our radiator manufacturers that I need to reject this much heat, and they will tell us, okay, you can use this much radiator, but there are a lot of tools to decide it. And we have hoses which connect all the components. All the arrows which you saw in the last slides, they are hoses. So you need to choose the right size of the hoses, right lengths, and right configurations of the hoses. Okay. So these things you will do here. So you will put together all the components. You will be having a water pump, you will have a battery, and you will have a radiator here. So you will put everything together. Okay. And next step, what you will do, finally, once you put everything together, you need to choose the electric water pump, which generally comes at the last stage. Okay. So when you put all the components and when the coolant flows through it, there's generally a pressure drop in the system. Okay. And it's again hydraulics. Okay. Generally the most common fundamentals we use in designing a cooling system is thermohydraulics. Heat transfer and fluid mechanics are the most important subjects which you need to learn if you need to have a career, or which you need to if you need to work on designing these systems. Okay, you need to estimate the pressure drop in the circuit, and based on the coolant pressure drop and flow rate, you will decide which e-water pump to choose. Okay, so once you decide the you know which e-water pump to use, you know the battery is there, you know which radiator is being used, which is decided here, you know the hoses which we are using today, the hoses. So we connect everything together, and then we do simulations, we do prototypes, we test, we see whether we are maintaining the temperature within 55 degrees Celsius. And if something is wrong, we again come back to the place where we missed out, whether we missed on the coolant, whether we need to increase or decrease the flow rate, or whether we need to uh, increase the size of radiator, or we need to use a chiller. So these kind of decisions we take here. Okay, after finalizing all this. So this is how cooling system design is done in general. These are the steps which we follow in general. Okay, you can go to any automotive industries, or you can go to any research industries, or this is how it will be done. Okay. And coming to the next part on the e-powertrain cooling system components. So as I said, you must be more familiar with these components already. So I will start with the components which you know already, which is, okay, this is a radiator, which we saw already. So it is e-powertrain loop of, I think, Tesla or BMW, I forgot. So this is the battery, okay? This part which you see here is the battery. And generally battery, over the battery we have this kind of aluminum channels. Okay, these are called cooling plates. So coolant will flow into it, and these plates will sit on batteries here, and it will remove heat from the battery. Okay, and those are battery cooling plates. And we'll be having electric water pumps. Okay, we will be having electric water pumps, and we'll be having all the hoses you see here. So these are the hoses, okay, and coolant hoses, and we'll be having chillers, as we discussed earlier, which is linked to the refrigerant loop, and the refrigerant is cooling the coolant. We use chillers, and we use radiators, which uses air as a medium to cool. This is a radiator; it uses air as a medium to cool. And this is a degassing tank. It's more of a storage of coolant, but it also has other functions. Okay, so generally in a car, in front side on the bonnet you'll be having the radiator, and on the passenger side you'll be having the battery. On the rear you'll be having the e-powertrain. Okay, imagine this is a car. This will be a car over the wheels. Car. Okay, on the battery pack will be generally on the underground of the passenger compartment. On the front you'll be having a radiator. On the rear, report will be placed generally. Okay, so this is how layout will be in a cooling system in general. Okay, and these are more or less examples of what we saw till now. Okay, so this is an AV of Porsche taken. Okay, I will explain you the parts which we discussed until now. So this is, as we see, it's the battery cooling plates. These are batteries not shown here, but these are generally cooling plates. Okay, cooling plates. These are cooling plates here. Under this battery will be there, and coolant will flow in these plates. Okay, coolant will flow here, coolant will flow here, and it will come out. Okay, and this is the e-motor. This is the e-motor. As you can see, cooling plate is under the car, and e-motor is behind the car, and you will be having the radiators here. I think this is also, I'm not sure what is this. So you'll be having e-water pumps here. You'll be having, the radiators. Generally, we have two different radiators. Okay, for example, one is LT radiator, which is low temperature radiator. If you can see here, LT cooler or LT radiator, and which is mainly used for cooling the e-powertrain and battery circuits, because they should be maintained at less than 65 or 60 degrees Celsius. We will have a separate radiator for IC engine, okay, where we need to maintain the temperature at higher, for example, 100 degrees Celsius as we see before. But this is a EV, it's not like a PHEV where we IC engine at battery cooling circuit board. So we have chiller here. As we have chiller, we have LT radiator with fan. So as you can see, these are the heat exchangers, and based on this, you can see what kind of layout they are using. Okay, they are using hybrid layout here in the which where chiller and radiator work in parallel, and only if we see in detail, we will know whether they're using any valves. So this is the example of Porsche taken, and this is an example of Audi e-tron. Okay, here again you can see there is a radiator here, and you have the battery cooling plate at the bottom. Okay, and on one mode they are cooling only using radiator. It's a hot liquid in, and you're having a cold liquid out. And in the second mode they are having a chiller here. It's not very clear, but they're having a chiller here where cooling via chiller. Okay, so instead of cooling via heater, the radiator is cooling directly via chiller. Okay, so this is the second example. You can always refer to these sources and you can get more information. And this is an example of Tesla Model 3. So as you can see again, this is the battery plates. As I can see, they are placed in the bottom of the passenger compartment, and you have the LT radiator here, and you'll be having chiller placed somewhere in this regions near. It's not very clear. You have chiller placed here, and you have the e-powertrain here and transmission units here. Okay, so this is the most common layout which you can see in all these things. Battery cooling plates will be placed in the bottom of the passenger compartment. The radiator will be in the front. You'll be having the e-powertrain loop in the front or in the rear, depending upon cars. And you'll be having the chiller units here, which will be connected to AC loop. You have the e-water pump here, which pumps the circuit through which pumps the coolant through the circuit. So these are the most common layout, and you can take any from any countries or any market. It will be the same. Okay, it will be the same layout. Maybe a small difference in strategies will be there, but you can always look out for more examples. This is very brief examples. And okay, so we have covered the concepts, and we have covered the most of the learning points today. And coming to the final slides where we discuss about career path. Okay, we generally have three different types of career paths based on your interest and based on your knowledge. For example, if you're more interested in numerical calculations, if you're more interested in simulations, you can always be a simulation engineer. Okay, simulation specialist or engineer in cooling systems. Okay, so whenever we design a cooling systems, and as a first step, it's in a very upstream or in a very concept phase, we will make 1D models. Okay, where we will estimate the thermo-hydraulic behavior of the system. We will put all this radiator, pump, chiller, batteries in a circuit, and we will check whether we are able to maintain the required temperature. We need to check whether we are able to maintain the required flow rate, whether my coolant pump is sufficient, whether my radiator is sufficient to maintain the temperature. So this kind of analysis is done in the very beginning. Okay, so this kind of engineers or this kind of knowledge has much more scope or very broad scope in the future, because today the automotive industry is moving more towards digital validation compared to physical validation, because physical validation takes a lot of money, it takes a lot of time, and it's very difficult to if you make a mistake, you cannot you need to spend a lot of cost to do it again. So they're trying to finalize everything at the beginning, at the simulation, at the virtual phase, where you can do a lot of studies. Okay, so the most common softwares used for cooling system study are AMSIM and GT-Power. AMSIM is nothing but Advanced Modeling Environment Simulations, and GT-Power is a pack of GT Suite softwares. Okay, so we do vehicle level simulations to evaluate the cooling systems, which means we will be doing aerodynamic studies. We will be integrating all the systems in a vehicle, like in the vehicle, and we will try to get the results at this condition, whether we are able to get the ambient or optimum temperature or not, is what we study here. Okay, so you can learn the softwares and it will be very helpful to you, and it will be very valuable knowledge addition to you, okay, in the future, because this is where the industry is moving towards digital validation. Simulation engineers or simulation specialists, you have a lot of values. Okay, and next step is the system engineers. Okay, so here what happens, system engineers generally define the cooling requirements of, the system of the vehicle. So they will say we have battery and we have e-powertrain, okay, and they need to say how much coolant I need in the battery, okay, how much coolant flow I need in the e-powertrain, whether we need to use a radiator, whether we need to use a chiller, what kind of heat exchanger to be used, what kind of cooling layouts to be used, okay. They need to size the each and every component. E-water pump, they need to size it. They need to size the, you know, radiator, they need to size the hoses. So generally, system engineer will be giving inputs to simulation engineers, and they will be doing simulations and giving results back to the system engineer. And again, based on the feedback, they will try to improve the system. Okay, so they are responsible for the whole system, which means they can do anything. They can do they can use any components, they can use layout, any strategies to keep the battery temperature within limit, which is 55 degrees Celsius. Okay, this is the main job of the system engineer. Okay, he has the control of overall system. Okay, so this generally comes at a bit later stage where you have knowledge on all the components. Then you work at a system level where you work with different teams, like a simulation team, you work with a radiator team, you work with vehicle team, and it's a very broad scope and it's a very interesting job, okay, which I'm doing today. So this is system engineer. And next comes development engineer. Okay, once we define the components, once we finalize the sizing, this is the component which I need to use, and I have did the calculation, found out it's okay, then I come to the development stage. Okay, so here is the stage where you will be dealing directly with the parts. Okay, until this stage you will mostly work with, calculations, you will mostly work with simulation tools, but you won't be having a real experience of the part. But as a development engineer, you will be developing this component physically. You will be making prototypes, you will be making you will be doing validation test, and those things to check whether component is right or wrong. And once you validate it in a prototype, then you will be going for mass production. Okay, then you to put in the vehicle, you will get a touch and feel of the components. You will, once you spend a lot of time as a development engineer, you'll be having a much more knowledge. And once after you become a development engineer only, you will be more moving towards system engineer. Okay, so this how the kind of career path which you can do in terms of battery cooling systems, and more general any mechanical component developments. Okay, and coming to job openings or job opportunities, as you can see, automotive EVs are trending thing today, and we are having a huge requirement. And there is a kind of knowledge gap where people need a lot of upskilling. So most of the companies in India and also in abroad needs people who are knowledgeable in EVs and more relevant to cooling systems. Okay, so companies like Mahindra, Tata, Hyundai, Renault, Nissan, and Mahindra. So all these, when a company is working on EV, they need a thermal management specialist, they need a thermal management engineer, and that's something that is wide open today, which you can go in and take it. And apart from OEMs, we also have tier 1 companies which are creating cooling system modules. For example, Mahindra will not create a cooling system module. They will only find out, they will have a system engineer. They will say how much cooling I need, what kind of components I need, and they will give the requirement to Bosch. Okay, and Bosch will in turn provide the components to Mahindra. Okay, so it's not only your opportunities in OEMs, you also have opportunities in tier 1 companies. If you have much knowledge about cooling systems and you work in Bosch, you'll be giving cooling solutions to Mahindra or Tata or all the automotive OEMs which are there today. Similarly, we have Valeo, Continental. These are the companies which have lot of scope today. They're working much more on EVs and cooling solutions today. Okay, and also these are things in India. not limited to this. There's always more options like upcoming companies. Ether Energy is there, Ampere is there. So lots and lot of opportunities are there for you. And in India, and coming to global scenario, you have ocean of opportunities where Tesla is in the leader of the market. Nissan is, all OEMs are working towards. Nissan has Leaf, which is the most successful EV today, and Renault has Zoe. Rimac is a supercar, super hypercar manufacturers where they do high performance EVs for racing, and Porsche is also doing high performance EVs. So this is the kind of opportunities there. There is a huge scope, huge ocean of opportunities where you can go in and contribute, and much more. And that's all from me today. Thank you.